Question 7 then, and this is thermodynamics. As we can see, we've got a classic PV graph. So let's get involved. The diagram shows 3 ways in which this much ideal gas can expand from this volume to this volume. So this is expanding. It hasn't got arrows on. I'm going to draw them on. There's 3 ways that it can expand. It can either do AX or AY or AZ. Finding temperatures at A and X then. So this is just ideal gas law. PV equals nRT. So T equals PV over nR. Be a little bit careful. One of the common mistakes students make is they ignore the units on the graph. So pressure here is in kilopascals, so 120 times 10 to the 3. Volume just in meters cubed, so that's just the base unit here. So 0.02 divided by number of moles, 0.9, multiplied by the ideal gas constant. And that comes out at 320.9. So 321 Kelvin. That's at A. I should really put in a little subscript. So temperature at X then is equal to 120 times 10 to the 3 multiplied by 0.06 divided by 0.9 over 8 times 8.31, and that should just be 3 times more, so 963 Kelvin. No problems there. Calculating work done over AX. Now AX is happening at a constant pressure, so no estimates needed here, no real need to think about it in terms of area under the graph. If we look at the formula sheet, we are given that work is pressure times change in volume, which of course is true for a constant volume. So easy enough. Again, careful with the units. 120 kilopascals multiplied by that change in volume, and that 0.44,800, and it's joules. This is an amount of work being done, so it is an energy. Yeah, so no problems there. Okay. Part C. So this is the 6-mark QER. So let's actually take some time to analyze this question a little bit. 6-mark QERs, remember, you're trying to get into a band. It's a top, middle, bottom band system for marking, and the physics that you put on the page will get you into one of those bands. The quality of your answer will choose whether you're the top or the bottom of that band. So what is it that we have to do here? Look at the way this is phrased for both AY and AZ. So straight away we can split our answer into 2 parts, one for AY and one for AZ. Compare work done, internal energy, and heat flow with those for AX, and that is in bold. So a comparison is what's required. So the way I would approach this question, the way I would go about this, I would literally write, before I'd even thought about what to include, I would put the structure of my answer down, and I would do it like this. AY, underlined. That's a heading. Work done. As my kind of first bullet point. Leave myself some space. Internal energy change. Leave myself some space. Heat flow. And leave myself some space. And then AZ and same thing. Because in this example, you know, the question has basically done this for us. It's told us what we need to include. And I think by putting these bullet points in, by setting it out on the page like this, you're going to make sure that you include the things that the questions ask for. You're not going to lose sight of that. That's what the question wants from us. So let's just put those down as headings. Note this bit in bold. Compare with those for AX. And we don't need to do calculations, but we must give a reasoning. So for each of these points, let's just make sure we're always in the back of our mind saying, how does it compare to AX? And if we state how each of these compares to AX and then justify it, surely then we get 6 marks. Because bear in mind, the QER bit is for a logical structure, etc. And a heading with bullet points is perfectly logical. So let's go back to the graph and have a think about what's actually happening here. AX happens at a constant pressure. So the internal energy has increased because it's at a much higher temperature at X than it is at A. So U has increased. The work that it has done is large because it's this whole volume underneath the graph, and it was at a constant pressure. So that is a lot of work being done. And therefore the energy, and remember this, what we're thinking about now is this equation, isn't it? The first law of thermodynamics. Q is therefore very large because enough heat has flowed in to this gas, not only to do this work, but also to increase the internal energy. For the internal energy to go up while work is being done, a lot of heat has flowed in, a lot of Q. So that's AX. Let's think about AY then and think about how that compares. AY, constant temperature, it says here, so U is constant. No problem. W therefore must be equal to Q if U is constant. So bear that in mind. The work done is definitely less than AX because the pressure decreases, hence the area under the graph is smaller, or however you want to justify that area smaller, that's supposed to say. And Q is therefore equal to the work done and is less than AX. In the case of AX, it was larger than the work done. Finally then, AZ, no heat in or out of gas, so Q is 0. U, internal energy has decreased because if Y is at a constant temperature, they both obviously started off at the same temperature, and Y has ended up at a higher temperature than Z. So U has decreased, whereas AX increased, and W is less than AX and AY, and must surely be equal to the decrease in internal energy. Whereas in the case of AX, W was less than the increase in internal energy. Sorry, yeah. The internal energy in AX increased is what I meant to say there. Size of it, actually I can't make a statement about without a calculation. So let's put all those comments in here and have a think about making sure in each case we always refer it to AX and what happened with AX. So first things first, work done less than AX. Less than AX, since pressure decreases, that's supposed to say decreases, area under graph smaller. Internal energy is constant, since constant temperature. And, you know, bear in mind, each step of the way we need to compare it to AX. Whereas, that was supposed to say, whereas U increases for AX. Heat flow, then heat flow is less than heat flow into gas. I'm going to mention that into gas less than AX equal to the work done. Whereas in AX, whereas for AX, heat flow is greater than work done. Because the internal energy went up. Okay, AZ then, same thing. I'm just shoving these kind of statements I've made up here into into these headings. So work done much less than AX. And less than AY. And again, I'm just going to put since smaller area under graph. That's how we're able to tell that. Or you could make reference to the pressure decreasing. Internal energy this time decreases. Since temperature decreases. My goodness, what's going on with my handwriting? And again, let's make sure we're referencing it to AX, whereas U increases for AX. And then finally, heat flow 0. Whereas heat flows in for AX. And I think that's it. So one last check. Have I done what the question has asked me to do? For both AY and AZ, yeah, I've got them both here. Have I compared work done, internal energy and heat flow? Well, my headings have made sure of that. And in each case, have I compared them in bold with those for AX? I've mentioned AX, 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 so yeah, surely that's 6 marks, and that's it.